Okay, so we've been talking about vector spaces, and we've been talking about uh, invertible linear transformations. And of course, invertible transformations uh, involve two vector spaces. For instance, we have a vector transformation here. We can also define a transformation here. So we can go backwards and forwards between these two vector spaces. In some sense, we'd like to say these two vector spaces are equivalent. So that raises a question: when are two vector spaces the same? Certainly here we have a mapping that takes us from one vector space to another and back again. Can we say in some sense that these two vector spaces are the same? So what do we mean by the same? We mean that they have the same structure. So in this section we're going to unpack this idea of what it means for two vector spaces to have the same structure. And we say that two vector spaces that have the same structure are called isomorphic. Now, if two vector spaces have the same structure, we should have some way of comparing one with the other. And that means having a way of going back and forth between these two isomorphic vector spaces. So isomorphism is a map between isomorphic vector spaces. Between isomorphic vector spaces. Okay. Now, iso means same, and morphic means form. So again, we're going to unpack this idea of what it means for two vector spaces to be the same form, the same structure. Okay, here's a definition. Isomorphic vector spaces. Two vector spaces are said to be isomorphic if there exists an invertible linear transformation, which is called an isomorphism, with domain U and codomain V. T goes from U to V. And we write this symbol, looks like similarity. U is isomorphic to V, and the linear transformation T is called the isomorphism. Okay. Okay, so let's look at some examples of isomorphic vector spaces. Think about P3 and think about M22. And here's a mapping from P3 to M22. We map this polynomial with 4 coefficients into this matrix with 4 entries. Now 4 coefficients, 4 entries, this seems to have some kind of surface similarity. It turns out that in fact this transformation is invertible, which can be shown by writing down a matrix for the linear transformation and showing that that matrix is invertible. And okay, so in that case, according to the definition, the third degree polynomials and M22 are isomorphic, and we have an isomorphism here between them. Now there may be more than one isomorphism between two vector spaces, as we shall see. Right, so what is isomorphism good for? Now isomorphism has certain consequences. For example, suppose I wanted to take a linear combination of two polynomials. And you could do this directly, or you could do the following. You could take the linear transformation of the combination. And we know that for a linear transformation, the linear transformation of a linear combination is the same linear combination of the transformed polynomials. Okay. So we could apply this transformation to the polynomials and discover two matrices. We could combine these two matrices, and then we could go back again and get the same result that we could have gotten if we had just combined the two polynomials directly. Okay. There's a picture for how this works, and this is a very common picture. You have two vectors in your U space, and here you have two vectors in your V space. And I can divide this up. This over here is the U world, and this is the V world on this side. Okay. And here you have the two vectors and you add them in the U world. You can take these two vectors over into the V world and find their images and add them in the V world. And it turns out that if you go back and forth between these two results, you actually get the translation of the same result. Okay. All right, now some facts about isomorphic vector spaces. One important fact is that if two vectors are isomorphic, then the dimensions are equal. And you would certainly think this would be the case. But that follows directly from things that we've shown. If two vector spaces are isomorphic, then there's an invertible linear transformation, which is both injective and surjective. If it's injective, then the dimension of the domain is less than or equal to the dimension of the codomain. We showed that earlier. And if it's surjective, then the dimension of the domain is bigger than or equal to the dimension of the codomain. So if we have an isomorphism, which is a invertible linear transformation, then we have the dimensions of the domain and the codomain are equal. Okay. All right, now we've been talking about invertible linear transformations, and we're going to go back for a second and talk about general linear transformations that are not necessarily invertible. We're going to talk about the rank and nullity of a linear transformation. Now, we've talked about rank and nullity of matrices. And I hope that you're seeing more and more that matrices and linear transformations are very closely related and can even be identified together. So a lot of the things that we said about matrices, we can also say about linear transformations. First, let's define the rank of a linear transformation. Given a linear transformation from the space U to V, then the rank is the dimension of the range of T. Now remember, the range is the part of V that's actually hit by the linear transformation. If we have a linear transformation T here, U may not map to all of V, it may only map to a part of V. So this is the range, and the dimension of this range is the rank. Now we know that the range is a subspace of V, so we know it does have a dimension. We can also define the nullity of a linear transformation. That's the dimension of the kernel of T. Now remember what the kernel is. The kernel is the part of U that maps to 0. Okay. It's quite possible that not just a single vector maps to 0, but a subspace maps to 0. We do know that the kernel is a subspace. So here we have two spaces, the range and the kernel, and they both have dimensions, and we call the rank the dimension of the range and the nullity the dimension of the kernel. Right, now first, if we talk about surjective linear transformations, we know that if a transformation is surjective, then the range is equal to the entire space V. So here we have U, here we have V, and if U maps to all of V, then it's surjective. Okay. So what does that mean? That means that the dimension of the range is equal to the dimension of V, or the rank of T must be equal to the dimension of V. So that's what this is saying. If T is surjective, then the rank is equal to the dimension of V. On the other hand, if we have an injective linear transformation, we know that the kernel is trivial. The only vector that maps to 0 is the 0 vector itself. So the kernel has dimension 0. So that means the nullity is 0. Nullity is the dimension of the kernel. So here we have that the nullity is 0 if and only if the map is injective. Okay. All right, now here's a theorem that ties a bunch of things together. We've just talked about rank, which is the dimension of the range, and the nullity, which is the dimension of the null space. It turns out rank plus nullity is equal to the dimension of the domain. Okay. Formally, let T be a linear transformation from U to V, then the rank of T plus the nullity of T is equal to the dimension of the domain. Now let me relate this to something that we saw with matrices. If you remember, when you had a matrix, we talked about the dimension of the null space, the dimension of the null space and the dimension of the column space, and the sum of those two is equal to the number of columns. Now, when you think about this as a linear transformation, the number of columns is equal to the dimension of the domain, because when you multiply this matrix by a vector, the number of entries in the vector must be equal to the number of columns. So the number of columns is equal to the dimension of the column space plus the dimension of the null space. The column space consists of column vectors. Now, what are these column vectors? These column vectors are vectors in the codomain. We're mapping from vectors of size equal to the number of columns into vectors with size equal to the number of rows. So these column vectors are vectors in the codomain, and the column space is the range. It's the range of the transformation that takes you from vectors of this size to vectors of this size. So here we're having column space, which corresponds to rank, null space, which corresponds to nullity. We have column space plus null space equals number of columns. Number of columns corresponds to the dimension of the domain. Okay. All right, so to prove this theorem, what you basically do is you construct a basis for the domain that consists of a basis for the null space, for the kernel rather, plus a basis that maps to the range of the linear transformation. I'm not going to go through all of the details, but what you essentially do is well, let's draw the linear transformation with u goes to v. And here let's take a basis of the range, v1, v2, v3. Now, since these vectors are in the range, we know that they're vectors w1, w2, and w3 that map to these v1, v2, v3. Now, we don't know that these w's will form a basis of u, and in fact they won't in general. What we do is we augment this set of w's by another set of vectors, which is a basis for the kernel. Okay, so we also have a set of basis vectors here that all map to 0. They all map to 0. Okay, so we have two sets of vectors, one set of vector that supplies a basis for the range, and another set of vectors that all map to 0 in the codomain. And it turns out that this entire set of vectors is a basis for the codomain. So you know you have to show two things. You have to show, first of all, that they're linearly independent, and then you have to show that they actually span the codomain of U. And those details you can find by reading through this proof. First, to show that they're linearly independent, you show that any relation of linear dependence must have all coefficients 0. So that's how you get, that's this part here. That's the first part up to here. Second part says, okay, now if I take any arbitrary vector in the domain, can I write it as a combination of w's plus u's? And what you do basically is that you find a vector that's a combination of w's that has the same transformation value, and then the difference between that vector y and the original vector u must be in the kernel, which means it's spanned by the u's. Okay, that's kind of sketchy, but you can read through the details of the proof. All right, now this is a powerful theorem for determining properties of linear transformations. Here's a particular example. Suppose I have a linear transformation from C6 to C6, 6 dimensions to 6 dimensions, and suppose I know that the kernel is trivial. What does that mean? That means that the nullity of t is 0. Okay. All right. So first of all, this means that t is injective. Second of all, we know that the dimension of the domain is equal to the rank of T plus the nullity of T. So 6 is equal to the rank of T. That's the dimension of the range. Dimension of the range is 6. That's equal to the dimension of the codomain. So what does that mean? That means that T is surjective, so T is invertible. So from this simple fact that we know the dimensions of the domain and codomain, and the fact that the kernel is trivial, has given us an invertible linear transformation. Okay, so let's stop there. All right, so here we want to tie together two strands of discussion that we've had throughout this book. Remember that we started out this book with systems of linear equations, and that really was the motivation for starting out with matrices in the first place. Whenever you have a system of linear equations, you can form a matrix, and vice versa. Now we're going to look in particular at the matrix of coefficients. So if we look at this example, arch type D, we can see arch type D is here. So the matrix of coefficients is this part here. You can see it's 2, 1, 7, minus 7, minus 3, 4, minus 5, minus 6, 1, 1, 4, minus 5, which is just the matrix here. So properties of this matrix correspond to properties of the set of solutions of this linear system of linear equations. Okay. We can define the linear transformation, which is this matrix times a column vector, x1, x2, x3, x4. Another way of writing that is in this way, as a linear combination of vectors. And when we're trying to solve this system of linear equations, you're trying to find the find the x1, x2, x3, and x4 such that this linear combination is equal to a particular vector. For arch type D, it's asking for this particular vector 8 minus 12 minus 4. You can look back there and see that what you wanted, whoops, let's do it again. Arch type D said 8 minus 12 minus and 4. Whenever you have solved system of linear equations, you are going to have some constant vector that you want your linear combination to be equal to. Okay. All right. Now, there may be more than one solution. In the previous discussion, we found one solution was 7, 8, 1, 3. That means 7 equals x1, 8 equals x2, 1 equals x3, 3 equals x4. But that may not be the only solution. We know from our discussion that the general solution is going to be a particular vector, such as this one, plus an arbitrary vector in the kernel of the linear transformation. So this kernel is a subspace which has a certain dimension. Okay, so we have characterized the solutions for a system of linear equations as a particular vector plus a subspace of vectors. And this is a general rule no matter when you have a set of linear equations. The solution will always be a particular vector plus some subspace, which is the span of a set of vectors. Okay. We can identify the solution for if dx equals d. That's the same thing as this LSDD. It's the pre-image of d. It's the inverse image of this linear transformation. Here t, I probably should put a d here because that's the matrix that you're applying. This linear transformation T is the transformation associated with the matrix D. Okay. All right, now, in this particular case, when we have a matrix like this, you can see that the number of rows is less than the number of columns. It turns out that the nullity of this linear transformation, see we're identifying this linear transformation T with this matrix T. The nullity of T turns out to be 1. We know it's at least 1 because you can't have, because the dimension of the column space is equal to the, the number of columns is equal to the dimension of the column space plus the nullity, but the dimension of the column space can't be bigger than the dimension of the row space. So in this particular case, it turns out that the nullity of t is 1 and the rank of t is equal to 3. So what does that mean in terms of the linear transformation? Well, let's write it down here where we have a little more space. If I draw my u and my v, I know that the kernel has dimension 1. So in here there's a kernel that all maps to one particular vector here. And I also know that the rest of this does not map to the entire vector space V, but only to a subset of V. Okay, so this whole vector space U only maps to a subset of V. It's not onto. And the dimension of the range is equal to 3. Okay, so there are some vectors which are not hit as the range in the range of this linear transformation. What does that mean? That means that for this system of linear equations with these coefficients, there are going to be some vectors, some constant vectors, for which there's no solution. In this particular case, there was a solution. In arch type E, if we go back there, okay, arch type E is here. Arch type E had a different constant vector over here, 2, 3, 2. And you can verify that, in fact, this system of linear equations does not have any set of variables that will give you this constant vector as a result. It's an inconsistent system, and what that means, according to our picture, is simply that this vector 2, 3, 2 is in the part of V that's not hit by the linear transformation. Okay, and you can go through this. When do a system of equations have a unique solutions? We know that's when the matrix is invertible, and we also know that that's when the dimension of the kernel is 0, and the dimension of the then the rank is equal to the dimension of the codomain. Okay, so we can relate these linear transformation properties to properties of the systems of linear equations. So it's good to keep in mind this identification. And with that, we'll finish this video.